Okay, so we're going to talk about distribution of the sample proportions in a hypothesis test. This video will be pages 174 through 177, the note spiral. So first off, beginning with the central limit theorem for means, states the sampling distribution of the expected values, in other words, the means of a population, will be approximately normal for any population, regardless of the shape of the underlying, if the sample is large enough. So if we have a large enough sample, the distribution of the means, distribution of the X bars will become normal. So distribution of the sample means will become normal. And in fact, we say X bar is an unbiased estimator for mu. So X bar is an unbiased estimator for mu. And so this will be the center of our distribution. And this will be the standard deviation of the distribution when we're talking about the standard deviation means. Obviously, if the standard deviation comes from the sample, we'll be using S divided by square root of n. This will be for a Z, and this will work for a T. Standard deviation of the population known versus standard deviation using standard deviation of the sample. But we have a condition. To be distribution of means, we had to have a sample is large enough, which is n greater than or equal to 30. Well, likewise, we have the same sort of thing for proportions. But in proportions, we have to have a sample being large enough, but NP has to be greater than or equal to 10, and NQ, which is the same as saying N times 1 minus P, also must be greater than or equal to 10, and we must satisfy both conditions. Also, in order to use that, we must have a random sample, but we had to have a random sample for central limit theorem. We need n less than 10% of the population, and NP and NQ, as we just said, both must be greater than 10. If we have that, then we say the distribution of the sample proportions follows a normal distribution with Z equals P hat minus P. We need to talk about P hat real quickly. P hat is the sample proportion, where X is the number of successes and N is the number of trials. So this is going to be successes over trials. And that's how that relates to the binomial. So P hat is the sample proportion. P is the claimed population proportion. And this is what we're going to believe to be true until we prove otherwise. And here we have P and Q and N. And this is really important to note that we're using P and Q here. So this is the population. This is not the sample. Real important to make that notation because it's going to differ depending on what we're doing. All right. So the center of our graph, if it's large enough, will be P. All right. That will be the center. When we talk about spread, and this is where things get a little bit weird, if we're working with a hypothesis test, we use the population. Why? We assume this to be true, and we already know it, so we're going to use it. If we're working for a confidence interval, on the other hand, if we're working with a confidence interval, our standard deviation is going to be P hat and Q hat from the sample. So this is the population P, and this is the sample P, which we call P hat. Now, the reason that's there is because we don't know what the population proportion is. We're trying to get an estimate for it, so we're having to use the sample proportion. All right, so let's try it out real quickly. Assume that 27% of the students at Reagan wear contacts or other corrective eyewear, and then we randomly select a sample of 110 students. So we are going to believe this, the probability is 0.27, that's the proportion. And we have an N of 110, and if P is 0.27, then Q is going to be a 0.73, which is just 1 minus 0.27. So specify the name of the distribution, etc. Well, the name of the distribution would be the binomial. However, we can use the normal approximation It approximates the normal. So the underlying distribution is definitely binomial. So the underlying distribution is binomial. However, we can use the normal approximation because our sample is large enough, and we know that because 110 times 0.27 is 29.7, and that's greater than 10. And NQ, which is 110 times 0.73, is 29.7, and it's not 29.7, that's incorrect. Need to make that correction. 110 times 0.27, or excuse me, So 110 times 0.73 equals 80.3. So this should not be 29.7. This is 80.3 is greater than 10. And please remember, this is just 1 minus the 0.27. So this is 80.3. That's also greater than 10. Both conditions for sample size were met, so we can use the normal approximation. Our expected value in this case is going to be 0.27. We expect 27%. And our standard deviation is going to be 0.27 times 0.73 divided by 110. There should be a decimal there. And that gives us 0.423. So this times this divided by this, P times Q divided by N, take the square root, and we get 0.0423 is our standard deviation. So it says, what's the probability that more than 30% of the sample use corrective eyewear? Well, first off, I need to do a couple things with that. For the calculator purposes, I'm going to need to calculate, well, let's go ahead and start with this. First off, our formula, as we said earlier, was going to be, let me get our pen, Z equals P hat minus P over PQN. So that's my formula. Well, P hat's 0.30, P is 0.27, this is 0.27, 0.73, and 110, so we plugged all our values in. And so when I go to the calculator, and I'm going to go stat test, and I'm going to go to one proportion Z test, which happens to be number 5. It says 0.75, that's my P. Then it asks for my X. They didn't give me my X, so I'm going to have to find it. Well, P hat equals X over N. So in this case, 0.30 equals X over 110. So if I exit out of that and I go 110 times 0.3, 0.3 times 110 equals 33. Now this is really important. X must be a whole number when you plug it in the calculator. If it's not, you need to round it. So stats test, one proportion Z test. So we had a P naught of, this was the claim, 0.27, and X where it goes 0.3 times 110, and you can check it right there. And as long as that's a whole number, it's good. If it's not, you need to round. N also needs to be a whole number. Our N was 110. And we wanted the probability that it was greater than 30%. And if we calculate, we end up getting 0.7087, and this is 0.2392. And this is a stats test, one proportion Z test for running a hypothesis test. All right, so couple things. Some of this is just review, and I'm going to expect you to read this, and this is on page 175. The purpose of a hypothesis test is to determine whether the data support a claim or not. And we always begin with the assumption that the null is true. And we are forced to accept a null or retain a null unless we have enough evidence against it. We don't prove the alternative. We do not prove the null. We're just forced to reject or fail to reject one. If we reject the null, then we determine that we're going to believe the alternative even though we didn't prove it. All right. Basically, once again, we didn't prove the alternative. We just believed that the null was false. And so we have, as a result, we're going to choose to believe the alternative. Our hypotheses are going to be set up as P equals the claim equals some value. This is going to be some number proportion. This will be some number proportion. Or P naught does not equal that, or P is greater than, or P is less than. Please remember, this is just going to be some value. This is for a one sample proportion that we're working with today. All right. And these are the graphs that would look like it. This would be the not equal graph. This is greater than because we're shading up, and this is less than. And we're going to be centered on P. And then we have our little P hats. Is P hat less than? Is P hat greater than? Or P hat not equal to? Alpha is still the area in the tails. All right. So if we had an alpha of 10%, this would be 0.05 and 0.05. In this case, it's one tail, so alpha is completely in one tail, as is this one. All right. So that's the area in the tails. All right, continuing on. When we look at our recipe for success, the claim equals some value, or the claim, or we're going to have the alternative not equal to, less than, or greater than. The next thing is define the parameter in context. Personally, I would rather this be number 1, this be number 2, and this be number 3. Sorry that they're out of order, but it's not required. What I like to do, I like to keep my normality as the third condition or the very last condition. We write the equation. Well, we do have a new equation, and it's not substantially different, because if we were working with the z, we say z equals x bar minus mu sigma divided by the square root of n. So p hat is our sample. This is our sample proportion. This is our sample mean. Population proportion, population mean, and this is our standard error. And this is our standard error here. Okay, so this is where the biggest difference comes in. The overall statements are generally the same, and I'll let you read those instead of taking your time. So moving on to page 177, we begin with our first hypothesis test scenario. A union spokesperson claims that 75% of union members will support a strike if their basic demands are not met. A company negotiator believes the true percentage is lower and runs a hypothesis test at the 10% level. So basically, there's a claim of this at the 10% level. So we have an alpha of 0.10, and they believe that it's lower, which indicates to me that this is going to be a less than. What is the conclusion if 87 out of a simple random sample of 125 union members say they will strike? So here we have our number of successes, and here we have our number of trials, and that's going to be important in just a little bit. All right. So the claim is that 75%. So P naught equals 75%, or P naught is 75% will strike. The alternative is will not strike. So P naught is the true population proportion of union members who will strike if their demands are not met. Now, I probably would shorten this up to P naught is the true population proportion of members who will strike. Conditions, random sample. They told us that there was a simple random sample, so that's given. They told us our sample size, or n in this case, is 125. 125 divided by 0.1 is 1,250. So it's reasonable to assume that there are at least 1,250 union members. Okay, NP needs to be greater than 10. And in this case, it's 87. all right? And they told us that 87 members said that they will strike. These are who will strike. So now we need to know those that don't strike. Well, that's going to be the number of failures, which in this case is going to be 125 minus 87, which equals 38. So 38 say they won't strike. And so the sample is large enough to use the normal approximation because both of these conditions are met. Okay, so when we write down our formula is going to be p hat minus p naught over p naught, q naught, and n. And this is z equals. Well, we know we have p, we know we have q, we know we have n, but we don't have p hat. How do I get p hat? Well, p hat is going to be x over n, or 87 over 125, which is 0.696. So I'm going to start plugging in. 0.696 is going to go right here. My initial claim of 0.75 is there. 0.75 also goes there. And then Q naught is 1 minus that, which just goes right here. So now I can go ahead and run this test. Stat test, 1 proportion Z test. P naught is 0.75. X has to be a whole number. In this case, it's easy. They told us it was 87. Our sample is 125. And our alternative was a less than. Press calculate. And we end up getting negative 1.39 equals 0.0816. So 0.0816 is less than alpha. So we are rejecting the null. All right. So because our p-value is less than 0.1, we reject the null. So our p-value is 0.0816. We reject the null. There is sufficient evidence that alpha equal 0.10 to suggest that the true population proportion of union members who strike is less than 75%. So at this point, we've learned how to do these really well, so we need to start putting them in common language. So after we've written our conclusion, and we always write it like this, simplified version says, we believe that 75%, less than 75% of the members will strike. We do not believe the union's claim. So this is a simplified version, and you now must include those. You must have the conclusion, and you must make it simplified, because this shows the reader that you actually understand it. Plus, now you're able to explain it to someone who doesn't know statistics. Because if I give this long statistical template, people don't understand it. So explain the meaning of the p-value in context and the type of error that may have been committed. Well, p-value, we always start off with our definition, is the probability that we get a test statistic this extreme given that the null is true. Please don't forget that given. All right. Why? It's a conditional probability. So if the null is true, or believing that the null is true, we have about an 8.16% chance. And that's what we say when we actually put it in context. Remember, the definition gets you no points, but this is a good idea to start off so that the reader knows you know what you're talking about. So there is an 8.16% chance that we'd get a test statistic this extreme in favor of the true proportion of union strikers being less than 75%, when in fact the null is true and 75% will strike. In other words, there's 8.6%, 1/6% chance we get a test statistic this extreme, saying union members, it's less than 75%, when in fact it really is 75%. So that takes care of the p-value. The next thing it asks for is what type of error. Well, we rejected the null, so the only type of error that we could have committed is a type 1, because a type 1 error is rejecting a true null. So what is it in this case? In this case, committing a type 1 error means that we mistakenly believe that less than 75% of the union will strike, when in fact 75% would strike. The consequences are that we're going to give bad advice to those negotiating a labor deal, all right, or something along those lines. Okay, the next video will concern confidence intervals.